Okay, in our previous class, we were speaking about the fact that it sometimes takes a long time for certain instructions to execute or to complete, and other instructions to take less time. So for instance, the jump instruction might take 200 picoseconds, and the load from memory instruction might take 800. And there are different reasons for that in hardware. Now, there can be different effects in terms of timing of different instructions on different architectures. And there are two main types of architectures that we need to talk about at this point. The first is what's referred to as a single cycle instruction architecture. And that refers to the chips that basically do one instruction, finish it, and then when the clock changes, it starts executing the next instruction. And when the next instruction is finished at the end of a particular clock cycle, the next instruction after that executes. So it's relatively straightforward. One happens after the other. And there are really good examples of these, like the Freescale Motorola or NXP HC11. That's a common processor from the 1980s, and its successor, the 9S12. These are both referred to or thought of as single cycle type of architectures, and they're fabulous microprocessors, and they were designed to do particular types of tasks, and they do it really well. Now, the problem with single cycle systems is that according to some people and for many different types of tasks, the single cycle approach can be inefficient, and there are more efficient ways of loading up your instructions and executing them and finishing them than just waiting for the next one on the next clock cycle. So it can be wasteful in terms of efficiency, and especially when the instructions become longer and longer or more complex, like floating point multiply. There can also be some waste in terms of the actual real estate on the processor, and that's another reason why single cycle has sort of a disadvantage now. But the real big advantage to it is that they're simple and they're easy to understand. So from a learning perspective or an execution, like you're designing something and executing it, these sort of processors are a really good thing because of their simplicity. Now, before we move on to discuss something called pipelining, we need to talk about computations or calculations regarding clock cycles and instructions. So when we're talking about the time it takes for instructions to execute on a computer or on a microprocessor, it's important to know how many instructions there are for a given program. So whatever you implemented in C or assembler, how many actual instructions there are, as well as you need to know what the average number of clock cycles per instruction there are for executing each of those instructions. If you multiply the two together, you can find out what the number of CPU clock cycles is for an entire program. So you can get a way, or you have a way of comparing one program versus another in terms of the number of instructions for a program and the clock cycles per program, or per instruction, sorry. And you can compare one architecture versus another in terms of their implementation. So the clock cycles per instruction, or CPI, is the average number of clock cycles each instruction takes to execute, and it's a way of comparing two or more different implementations of the same architecture, and that's where the A comes in for the ISA. So you might have, for a particular type of instruction class, you may have in one implementation one CPI, you might have 2 clock cycles per instruction, or you might have 3 or more, and that's entirely possible. Now, we have something called the performance equation, and basically what you do with that is you say that for the number of instructions that you've got in a particular type of program, you multiply it by the number, the CPI number, and you multiply that by the actual time it takes to complete a clock cycle. All right, so that's the period of the CPU clock. The other way of addressing this in terms of trying to calculate the CPU time is, instead of using the clock cycle or the period of the clock, use the clock rate. And so whereas the clock cycle would be in picoseconds or nanoseconds or milliseconds or something like that, be in terms of seconds, your clock rate would be in terms of something like hertz. It's 1 over seconds, basically. So basically what you got here is instruction count multiplied by CPI multiplied by clock cycle, or you take instruction count multiplied by CPI and divide by the clock rate. Either way, you get your CPU time. So the amount of time it takes to execute a particular program with a known number of instructions. So these equations separate the key factors that account or affect performance. They can measure the CPU execution time by running, you can measure the CPU execution time by running the program. You normally know what that clock rate is, and in the case of the PIC32, you've seen how to set it to different values, whether it's 40 megahertz or 80 megahertz or 5 megahertz. You can measure the overall instruction count by using simulators, so you can do that as well. And you might, in those particular cases, not actually know what the final CPU clock speed is going to be, or the clock frequency. And the simulator itself will typically work not in terms of hertz necessarily, but in terms of number of instructions per clock cycle, or the number of clock cycles it takes to implement. The CPI itself varies by instruction type, and as well as the architecture implementation. So you can have different chips that have different implementations of the architecture, and that will all change the CPI for the sort of calculation that you need to do. And if you have a question like this on the final exam, you must know what those implementation details are. They would effectively have to be given to you. Okay, so we spoke about a single cycle architecture like the HC11 or the 9S12. How could you change the architecture to make it faster? That is, to execute more instructions over a certain period of time. And the way to do that is by fetching and executing the next instruction before the current one has completed. And this is really sort of like juggling, where if you've got 3 balls that you've got to throw up in the air, you don't wait for the first one to land before throwing up the other balls into the air. You have them at some given point in time, sometimes all 3 balls, or if you're juggling more than that, more balls than that up in the air. And pipelining is similar to that. Effectively, it means that you can have multiple instructions being fetched and decoded and executed, and the results being stored all at the same time, or at least in different time slices. Pipelining is very common. This is what we call it. Pipelining is very common for most, not all, most modern processors. And so for modern processors like the 9S12, or sometimes call it the S12 series, these are embedded processors that have special requirements for latency and determinism. You won't have pipelining. But in a lot of processors like ARM processors and x86s and things like that, you do. It's important to, like I just mentioned, remember in these cases when you're comparing them, the CPU time instruction, or the CPU time calculation. So under ideal conditions and with a large number of instructions, the speed up from pipelining is approximately equal to the number of pipeline stages. So if you've got a 5-stage pipeline, then the speed up in terms of instruction completion will be 5-fold. So a 5-stage pipeline is nearly five times as fast as a non-pipeline system, because you can execute basically all these instructions 5 times faster. Basically, at the end of the day, you are fetching and executing more than one instruction at a time, and this relates to something called superscalar processing, which includes having almost parallel processing going on inside of your processor by having multiple components that can take instructions and deal with them. So let's take a look at what pipelining is. So pipelining is similar to what would happen if you were doing laundry. So in a regular laundry doing kind of scenario, you take your laundry, you wash it, you dry it, and then you fold it. The next batch is waiting for you, and when you're done with the first one, you start the next batch of laundry. You wash it, you dry it, you fold it. You finish folding that second batch, you take your third batch of laundry, you start washing it, drying it, folding it, etc. When you pipeline it, you're compressing all of this, and you're taking into account the natural parallelness of the system in order to speed things up. So for instance, if you take your first batch of laundry, you put it in the washing machine, you take it out of the washing machine, you put it in the dryer. Your washing machine is now free to be used again. And so you take your second batch of laundry, you put it inside of your washing machine while the other batch is drying. When the other batch is finished drying, you start folding it. The dryer is available. You now put your wet laundry into the dryer while you're folding, and you do that. Now your washing machine is available again. It's empty. So you take your third batch, you put it in there, and so on and so forth. And so it is a more efficient way of dealing with multiple loads of laundry. It takes more thinking and more planning, but it means that you'll be done in a whole lot less time. So instead of going until midnight to do your laundry, you can be done by about 9:30, just in time for your latest episode of The Walking Dead or something like that. Okay, so moving on, we need to quickly review the 5 stages of, say, a particular instruction like loading. So for load word instruction, in the first cycle of the CPU, then you're going to have to do your fetching. Second cycle, you're going to be doing some decoding of the instruction, executing, so you're involving the ALU, for instance. Then there's some memory reading, and then you're writing it to the register block. So these are the 5 stages that you would want to go through. So pipelining allows us to start the next instruction before the current one has completed. So effectively, from the laundry example, it means that we get to start using the washing machine as soon as the dryer is being engaged. So we can have better efficiency of executing a whole lot of different instructions or trying to get a whole lot of laundry done. So pipelining improves the throughput, so it means that the number of instructions that we can do overall over a given amount of time is better. It doesn't mean that it takes any less time to execute any given stage. So for instance, drying your laundry is still going to take the same amount of time for a batch of laundry. Washing your whites or your socks is going to take the same amount of time for both a pipelined and non-pipelined setup. But in terms of overall amount of laundry that you can do, it's better. So you get better throughput, you get equivalent latency, or the amount of time that it takes. So this is how pipelining would sort of look. We're going to make a little switch right here. We're going to say this is going to be the R type, and this is going to be a store word. So in order to set this up, what we do is we do a load first, and then there's a fetch, decode, execute, change memory or read memory, and then write to the registers. As soon as you've fetched the instruction for load word, you can fetch the instruction for the addition, for instance, that you need to do. As soon as you've finished fetching that second instruction and you've started decoding it, you can begin the process of storing the word of data that will result from the R-type instruction. So you do fetch, 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 decode, decode, decode. And so while the decoding phase in the store word is happening, you are executing the R-type instruction and you are reading from memory on the load word instruction. There's no conflict between any of these 3 because they can all be run effectively in parallel if they are time shared effectively. So the clock cycle, or the pipeline stage time, is limited by the slowest stage, and each one of these is a stage. So this is a stage right here, that's a stage right there, and this is a stage right here. For some stages, they don't need the entire clock cycle, so some stages will require half a clock cycle. And for some instructions, some stages are wasted cycles. Nothing happens in a particular stage at all, and we have to wait for something to happen. And that happens as well. Okay, so now we need to compare a single cycle to a pipelined type of architecture. So if we assume that for a given instruction in single cycle, so the simplest way we can do this, it takes 800 picoseconds to complete an instruction. So we're going to break it down. For instance, for a load word in single cycle, you have 200 picoseconds for a fetch, 100 picoseconds for decode, 200 for the execution. Then you have 200 for the memory read or write. In this case, it would be a read. And you have 100 to read to the register because it's fast. So in total, you would have 800 picoseconds for a typical instruction like a load word inside of a single cycle architecture. Now, for a pipelined architecture, and in this case, we're assuming a 3-stage pipeline. So a 3-stage pipeline, and any of the instructions like this decode right here and the write to register at the end has to be stretched out from 100 picoseconds to the maximum cycle of 200 in order for everything to line up properly. So that means that for your load word, it now goes from 800 picoseconds to 2 plus 2 plus 2 plus 2 plus 2. It goes to a total of 1,000 picoseconds. So each of these instructions, this is going to be the R type, and that will be the store word. It takes 1,000 picoseconds for the load word. It takes 1,000 picoseconds for the R type instruction like add, and it takes 1,000 for the store word. The difference in the end is that what you end up having is that for 3 of these instructions to occur, you have first a fetch of the load word, then you start decoding the load word instruction. As soon as the decoding starts happening, you can fetch the R type instruction. Once the execution starts on the load word, the decoding on the R type can start, and you can fetch the store word. And this is how it basically continues on and on, to the point where from here to there, it takes 1,000 plus 200 due to this, plus 200 due to that portion right there, for a total of 1,400 picoseconds to execute all 3 instructions in the 3-stage pipeline. So the follow-up question would be in terms of like throughput. How long would it take to execute 1,000,000 add instructions where you had a load word, an R type instruction for adding, and then a store word? So in the case of a single stage system, it takes you 800 picoseconds. So it's 800 multiplied by 1,000,000. Oops, right there. Okay, and that would be for the single cycle. For the pipelined version, it takes you 1,400 picoseconds to load up or fill the pipeline. But from there, once your pipeline is filled, every new instruction effectively only takes you 200 picoseconds incrementally. And so you multiply that by 1,000,000. Okay, and so you can see that in the end, for the pipelined version, this is going to be much faster to execute 1,000,000 instructions, and this is going to be slower. And how much slower? Well, effectively, after 1,000,000 instructions, it is a 3 times speed up. Put it over here. This is going to be a 3 times speed up in terms of the amount of executions that you can do per clock cycle. So it's actually really fast. Okay, so pipelining the MIPS architecture is made easier by the fact that all the instructions are the same length. They all are 32 bits. So that helps with the architecture, the hardware implementation. So we can fetch in the first stage and decode in the second stage these 32 bits. There are very few instruction formats, effectively only 3. And we've spoken about those 3 instruction formats. And there is some similarity between these instruction formats in terms of decoding them. So the decoding can always happen in this second stage. And it makes it relatively straightforward. And you've seen that from the drawings of the hardware flow data, okay? Memory operations occur in loads and stores. So any access to to memory itself is happening with a load word or a store word or one of those similar functions. Each instruction writes at most one result and changes the machine state once, and does it in the last of the pipeline stages. So we know when it's going to happen with respect to other instructions or sub-instructions, stages or cycles. And the operands must be aligned in memory, so single data transfer takes only one data memory access, and that's really important as well. So all of this means that we have simplified the whole process of fetching, decoding, executing, and storing of the result of these different operations. So it makes pipelining relatively straightforward. Okay, so now what we need to talk about is what happens with respect to pipelining and how the control signals are going to be broken up over time with respect to executing different aspects of an instruction, okay? And the way this is done is by talking about something referred to as state registers. And these state registers are these blocks. You can see them. There's one right there. You got another one right here. You got another one right here. And you got another one right here. And what these things are doing is they're helping to break up the flow of data. Remember, we talked about how the data flows more or less from the left-hand side here to the right-hand side here. And the control signals will change at each of these individual isolation blocks. Okay, so in terms of instruction fetching and decoding, then there's going to be some special magic that goes on at this stage between the instruction memory block and the register file. For some of the decoding and the executing, there's going to be another state register right here that is found between the register file and the ALU. And that will be involved or will work with any of the subtasks that are related to decoding and executing. Then you've got execution and memory access state register right here that is found between the ALU and data memory. And so as you move through the pipeline and you need to execute, you get out of the execution stage and into the memory stage, this portion right here will kick in and change its state to allow the flow of data from the ALU into the data memory without getting in the way of a previous previous instruction that was already in the pipeline and moving a little bit earlier. And then finally, you've got this memory and register write state register that kicks in when this particular instruction is ready to send information, for instance, from data memory all the way back into the register file. But effectively, if you want to think about this, these state registers are similar to locks in a canal. If ever you've been to Ottawa and seen the Rideau Canal and how boats are allowed to flow through at different stages of the canal, and they have to wait at particular stages until the locks open up to allow the boat to flow through. These are effectively like locks in a canal. So this would be a lock right here in the canal. This would be a lock in the canal. This would be another lock in the canal, and another lock in a canal. And your boat, little motor on the back here, would flow. Let me see if I can do this. Oh, like that. And it would flow through the canal. It would stop here. And then when it's allowed to pass through, it would stop here. And then the lock would open up and it would flow through here. And then it would stop. And then it would flow through there and then onwards. At each step, it allows for stopping and flowing in a controlled manner. And this allows different instructions that were in the pipeline already to go through in this controlled manner without stepping on each other or bumping into one another. Okay, and so this isolation is really important as you allow data to flow through. And the other thing to recognize is that each of these stages needs to be connected to the system clock because everything needs to be synchronized. So the system clock right here And this is the system clock that you control in the PIC32, for instance, using those pragma statements. The system clock allows the coordinated synchronization of those different locks, or those different stages or state registers with the program counter to allow data to flow through in a nice orderly fashion. Now, the control path, which we've spoken about before, is also a little bit trickier with pipelining. And so all of the control signals that we've been speaking about, and remember there's this control block right here, and you've seen this before, all of these control signals can be determined during the decoding phase, and this happens after the instruction fetch stage. So we fetch the instruction from instruction memory, and then we have to decode it. And once it's been decoded, then the result of that decoding can be loaded into each one of these state registers. Remember, the state registers are, here's one right here. There's another one right there. And these state registers are found between different stages, and they allow the flow of data to occur in a nice, logical, and controlled manner. That controlled manner is controlled not only by the clock, but by this control block that synchronizes things together. The signals that come out of that control block get distributed at different points in time, or executed in the state registers at different points in time. So we have the instruction fetch, we have the instruction decoding stage, and so you have these you read the instruction memory and you write on the program clock, and that never changes. During fetch, during decoding, there are no optional control signals. You're just decoding these control signals. Now, when you get to the execution stage, and then the memory stage, and then the write to the register file stage, then the different control signals, and you've seen these in the earlier talk. These different control signals that are sent out of the control block engage, and they have different values for different instruction types. Okay? And remember that 1 is a logic 1, 0 is a logic 0, X is a don't care. It could be any value, it doesn't really matter. And so those engage at different points in time, in different stages, in order to make sure that the flow of data is correct for the particular type of instruction that we are executing in that portion of the pipeline. Okay, so sometimes it helps to graphically represent a pipeline in, for instance, a MIPS architecture. And this helps us answer questions like, how many cycles does it take to execute a particular piece of code? What, for instance, would the arithmetic logic unit be doing during one of the cycles, like cycle 4? And if there's a hazard, okay, we'll talk about that in a second, why does it occur, and can that be fixed? All right, so it's important once again to remember that we're complicating things because the pipelining is great for performance in general processing, okay? So it's really good. Now, there are certain details that are important to point out. The first is that pipelines need to be filled. And if you've got a 4 or 5 or 6 stage pipeline, then you need to put 4, 5, or 6 instructions in it, and then it works really well. And so it takes time for that initial filling of the pipeline to occur. Once the pipeline is full, then effectively we can think of one instruction is completed in every cycle. Okay, so the cycles per instruction becomes 1 once that pipeline is full. If the pipeline blocks or needs to be refilled, then that complicates things. So we typically think of the best case scenario, but in the event that there is something referred to as a hazard, then you may have to flush the pipeline or modify the pipeline or something like that. So here are the different types of hazards that are typical in a pipeline system. The first is structural hazards. And this is when you attempt to use the same resource by 2 different instructions at the same time. Okay, so if, for instance, in the laundry situation, you try to use the washing machine twice or together at the same time by 2 different loads of laundry, you can't do that. That's bad. Data hazard. attempting to use data before it's ready. So attempting to use the wet laundry before the washing is done and putting it into the dryer. You can't do that. So an instruction source operand are produced by a prior instruction, and that instruction is still in the pipeline. Your control hazards are attempts to make a decision about a program control flow before the condition has been evaluated and a new program counter target address has been calculated. And we find this a lot, and this is really tricky with branches and jumps and what are referred to as exceptions. Exceptions are interrupts. And normally you can resolve these hazards by simply waiting or structuring your waiting in a particular type of way. So pipeline control must detect the hazard, and it needs to find out how to resolve the hazard as well. Hazards occur, you have to design for them. So one example of a potential hazard would be something like a single memory where you read and write to it, and this is the memory outside of the register file. So that, if you had one of those, it would lead to structural hazards because you would potentially want to read and write from that same piece of memory or that same memory chip or section of memory at the same time. And so if you are trying to read data from memory and read instructions from memory at the same time, and your controller for memory or your two separate memory chips can't account for that, then effectively you've got a conflict over resource access, and that's a bad thing. That's a structural hazard. You can fix this with separate instruction and data memories. And this is what happens in MIPS, that we have one section of memory that is controlled and accessible only for instructions, and we have another section of memory that's really accessible separately for data. And that helps resolve the potential for these sort of structural hazards. Okay, now your register file access, it is a single block of memory basically, and you can have problems with different instructions in different parts of the pipeline trying to access the register to read at the same time, or read and write, or write at the same time. You can fix register file access hazards by doing reads in the second half of a cycle and writes in the first half. So if a typical cycle takes 200 picoseconds, and so that's like a fetch or something like that. If your register read-write is only 100 picoseconds, okay, so this is 200 right here, then it means that you can block off your register access for one portion of the pipeline to the first half of that 200, and then the other instruction can access it in the second half. So you got a first half and a second half, and then allows you to access your register at two different points in time. Okay? And that's a really good thing. So you got your first half right here. So on the bottom half of the clock and on the top half of the clock. Okay, so the clock edges, a falling edge and a rising edge, allows you to figure out that particular state control. Okay, so having these clock edges, super important. So if your regular instruction is only on rising edge, for instance, the access to the register at these two different stages could use both rising and falling edges. Okay, from there, backwards dependency can be a problem as well. So that's trying to access, anyway, we'll show you in a second here. So dependencies backward in time can cause hazards. So if, for instance, in a normal case, you needed to access a register after some addition had happened over here, no problem, that's all good. However, if you were doing something with a register here and you needed that same information over here and over here, that's back in time. Okay, so that's negative time. You can't do that because time only moves forward, positive time. So that would be a hazard because we can't time travel. You can also have issues with loads. So we're talking about registers before. Loads can also cause issues. So if you need to have access to something after a load has occurred, like in this case right here, no problem. However, again, just like in the earlier case, if you've got a register that needed to be accessed before a load had loaded the register, then you've got a problem. Branches, that's another issue altogether. Branches and jumps can have issues if the conditions by which the branch needs to happen requires data that isn't available. You got an issue because it hasn't been calculated yet. And so if you have a dependency on an early point in time, so backwards in time for a branch condition, that's a hazard. All right. So there are workarounds for some of these hazards, and I spoke about one in terms of time slicing effectively a register access. You can do things like trying to make the clock twice as slow and taking instruction and trying to have it take 2 cycles instead of 1 to overcome particular issues. What if data memory access is twice as slow as instruction memory? Well, you can make the clock twice as slow, or you can let data memory access take 2 cycles and keep the same clock rate. So those are sort of workarounds if you need to. There are other, instead of just MIPS, there are other architectures, okay, like the ARM7 and the X scale and others that have different types of pipeline alternatives. But basically, the method that you've seen with MIPS is pretty straightforward and standard. Okay, so in summary, most modern day processors use pipelining to one degree or another. Pipelining doesn't help with the latency of a single task. So a single task will take just as long, or maybe even a little bit longer, but it does take the throughput of an entire workload, so many instructions over a long period of time, like 1 million instructions. You'll see a good reduction in the amount of time it takes for an individual average instruction to get through. And so you can get more instructions through if you're using pipelining. You can get absolutely a potential speed up with pipelining. That's fabulous. And pipeline rate is limited by the slowest pipeline stage. That's always important. So unbalanced pipe stages make for inefficiencies. So you want to make sure that things are nicely balanced out. And that's why we did the trickery back there with taking individual stages that took 100 picoseconds and we stretched them out, or we allowed portions of it to be stretched out to 200 picoseconds to help, for instance, with things like handling hazards. The time to fill the pipeline is important, and the time to drain it as well, which is the mirror image or the mirror condition, can impact the speed up for deep pipelines and short code runs. So if your code is really short, or if the pipeline has 20 stages or 25 stages, the time it takes to fill a pipeline or to exit that pipeline to drain it can be significant. And that's important when you're taking a look at benchmarking for different processors. As well, hazards are not optional. They occur all the time, and you need to design for them. Okay, and stalling, which is one potential way of dealing with it, can negatively affect the CPI. And so it's just important to keep that in mind, that there are ways to deal with pipeline hazards, and you just don't ignore it. You deal with it in your design, and you account for it. Okay, well, there you go. That is mostly what we wanted to discuss in Chapter 4.